Suppose I pick two random numbers between 0 and 1, say 0.27 and 0.81, and I take the maximum between those two. Then I do that again and again, maybe a few thousand times. Obviously, the numbers I keep are going to lean toward 1, because I'm always throwing away the smaller one. But now, let's do something completely different. Pick just one random number between 0 and 1, and take the square root. Do that thousands of times as well. And somehow, you get exactly the same distribution. Not approximately the same, but exactly the same. Which is weird. These two processes don't seem like they should have much to do with each other. So why do they? So, let's start with the first process. We pick two random numbers between 0 and 1 and keep whichever one is larger. Now, instead of asking what the maximum actually is, let's ask a slightly different question. What's the chance that the maximum ends up somewhere below this number a? Well, if either of our two numbers goes past a, then the maximum goes past it as well. So that wouldn't work. So for the maximum to stay below a, both numbers have to land below a. And there's a really nice way to picture that. Instead of thinking about the two numbers separately, we can use them as coordinates. The first number tells us how far across we go, and the second tells us how far up. So every pair of random numbers becomes a random point somewhere inside the square. Now, let's look at the condition we wanted. For both numbers to be below a, our point has to land somewhere inside this smaller square. Its width is a, its height is a, so the area is just a squared. And since the area here corresponds directly to probability, the chance that our maximum is below a is just a squared. So that basically sums up the whole secret behind the first process. Now, let's look at the second process. We pick another random number between 0 and 1, but this time we take the square root. And just like before, instead of asking exactly what value we get, let's ask a threshold question. What's the chance that the square root ends up below a? For this to happen, our original u has to satisfy a certain condition. If square root u has to be below a, then u itself has to be below a squared. And because u was chosen uniformly between 0 and 1, the probability of landing below a squared is just simply the length of this interval, which is a squared. So the square root process gives us the exact same probability expression as the maximum process. So this wasn't really a coincidence involving number 2. There's a much more general pattern hiding here. Suppose instead of picking two random numbers, we pick 3. For the maximum to stay below a, all three numbers have to be below it. Each number has a probability a of landing below the threshold, so with 3 independent numbers, the probability to all of them do is a cubed. Now take one uniform random number and take its cube root. For its cube root to be below a, the original number has to be below a cubed. So again, the probability is a cubed. So the maximum of 3 random numbers has the same distribution as the cube root of 1. And there's nothing special about 3 either. If you choose n independent random numbers between 0 and 1, then for their maximum to be below a, every single one of them has to be below a. That happens with probability a power n. And taking the nth root of one random number gives us exactly the same thing. So in general, the maximum of n independent uniform random numbers has the same distribution as the nth root of 1. And that's what was hiding behind our original experiment. Taking the maximum and taking a root seem like completely unrelated operations. One compares several random numbers, the other transforms just one. But if you ask how likely either process is to land below any particular value, they always give the same answer. That's enough to make the distributions identical. The same idea works for any number of random values, and I think that's the interesting part. Two random processes can look completely different, but still behave exactly the same.